Hello, hello. Hopefully everything is working. If you're watching this after the fact, make sure you check the description below for time codes. This stream is typically like 2 hours long, so you can check the time codes to skip around. Nice. Mark just got a CircuitPython board going. Let me pause my windows here. Sorry I'm a little late. Took me a smidge longer than I expected to get everything going, so. But we're going. And I think everything is going okay. Let me know if it's not. Audio is good. Thank you, David. Thanks to David for taking notes, as always. And we'll get the show on the road here. I'm kind of tired. Minnesota Mentat said, missed you last week. Thank you. Oats and Honey, the link to the stream, you can't hear me because you're my volume is a little low. I can move it up. Is that better? Maybe not. I can turn it up here too. Test, 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 test. I'm kind of a loud person, so I don't want it to be super loud, otherwise it'll clip. All right, let me say hi to folks, and then we'll do housekeeping, and then we'll dive right into the stuff I've been working on. Hello, Bruce. Hello, Unexpected Maker. Hello, Beata. Hello, Minnesota Mentat. Hello, Linux 203. Hi, Todd Totter. Thank you all for being in the YouTubes. In Discord, we have Keith the EE. We've got Mark Gambler. We've got DCD, Love the Factory, Oats and Honey, Dexter Starboard, and Doctor. So hello, everyone. Compared to other videos and streams I've been listening today. I mean, I'm hitting the red on OBS, so I don't think I want to push it too much more. Okay, so let's do housekeeping. Hello, everyone. My name is Scott, and I work for Adafruit on CircuitPython. Adafruit is an open source hardware and software company based out of New York City. I am here in Seattle. The sun is out and causing it to be a bit bright in here. I work remotely for Adafruit, technically as a contractor, and I work on CircuitPython. So CircuitPython is a version of Python designed for microcontrollers. Here's Unexpected Maker's board here that has a Wi-Fi capable microcontroller on it called the ESP32S2. You plug it in, it shows up as a drive, and you can edit the files, the code.py file on the mass storage device there, just like a USB drive would. So CircuitPython, that's what it is basically. If you want to support me, you can do that indirectly by supporting Adafruit. They pay me to do these streams by going to adafruit.com and purchasing stuff there. If you want to chat with me and a lot of others outside the bounds of a stream, we're always available on the Adafruit Discord server, which you can join by going to the URL adafru.it/discord. And so that's Discord. This is a deep dive. It happens nearly every week. I took last week off. It's normally Fridays at 2 p.m. Pacific, which is this time. But it's occasionally shifted to Thursdays at 2 p.m. if I want to do it, but not on Friday. Typically goes for 2 hours or more, and questions are welcome. So feel free to ask me questions. We've had lots of really good topics come up. Thank you, or from questions from the audience. So thank you to everybody who's asked questions. Unexpected Maker's board is the Feather S2. Unexpected Maker Feather S2 is on the circuitpython.org/downloads page. Thank you, Doctor. I used to warn about the cat being epileptic, but he's been doing so good, I think I'm going to actually take that off my list here. Hello, Deshipu. Hello, Simon. Simon asks how my break was. It was really good. We did a quick trip down to South Carolina to see a friend. The weather was beautiful. Got to wear shorts. Yeah, it was very pleasant. Good to take a break. Hello from Sweden. I started watching you from your 1-minute videos and got pretty interested. Would you please explain the topic? Yeah, so this will not be a 1-minute video. This is more going to be about a 2-hour video. But it is deep dives are all about the low-level stuff that I'm working on for CircuitPython. Today we're going to take a look at, continue looking at the low-level bits of the Raspberry Pi. Not the Pi Pico, but actually the proper Raspberry Pi. They are more complicated systems on a chip, and we're going to take a look at those. I think I'll open the window here because I'm already starting to get hot, and we just started. But yeah, so specifically I want to show off the SVD files, which are these system view descriptions, and then we'll also talk about interrupts. A asks, what education courses did you go to get to this point? So my background, for those of you who are new or haven't heard this, is I started learning programming in 2002. I was self-taught based on a book. And then I went to a university. I went to the University of Washington for 4 years, got a computer engineering degree there. I worked at Google for 6 years after that. And then I took a year off to do my own thing, which was embedded programming for drones. So I did board design and porting some open source software to work on the drone. Yeah, go Huskies. And then that was, I left Google in 2015. 2016, I joined Adafruit, and they had MicroPython on their radar, but MicroPython did not run on their main chip that they used in a lot of their stuff, and they hired me to do that. And that grew into CircuitPython, and we've been doing that for 5 years now, which is super exciting. It's come a long way, and now we're trying to bring CircuitPython to the Raspberry Pi. First, let me open my window. I think I might have enough cable to do it without. It's fall now, so I don't know, I can usually get away with the window being closed. But then again, I get all amped up for these streams. Okay. So let me just get caught up on the Discord here. Thanks for the links. Hello, JP Constantinou. Hi, Ask Patrick. A big Adafruit box with all the CircuitPython posters. That's awesome. Yay for interrupts. The cat in the cat cam, you can kind of see his reflection. He's between the cardboard thing and the window. He's just got him from a shelter or a rescue place, not from a shelter. Do I miss working on drones? Not at all. Unexpected Maker asked me that. I was not a huge fan of the community that we had around the drones. It's a lot of men, a lot of dudes. And what I discovered by doing all of the drone work was that I liked embedded. It was less so the drone part and more because to fly drones you need a lot of space, and I live in the city and that's kind of hard to come by. But I discovered that I really liked embedded work, so that was really good. And designing boards and stuff was really fun too, which I do occasionally. Well, actually, I think I got the overhead working, so we'll talk about a board I just designed, which I do kind of in my spare time. Linux 203 asks, was the chip you ported the samd-21? Yes, exactly. That was the chip that I ported MicroPython to. Yeah, so the very first thing we started with was a pretty large project for that. But I was so excited about it that I got the basics going pretty quickly. Keith EE says, board design is something I need to give a shot at. Where would you recommend starting for board design? KiCad, obviously. KiCad is an open source ECAD, so electronic computer aided design, drafting, design program that I use and recommend for, there's 2 stages to board layout. There's like schematics. And then once you have schematics, you can do the PCB layout, which is like how you actually draw the traces on the board. Contextual Electronics has videos of KiCad. And then Oshpark is my go-to for how do you get it manufactured. Oshpark charges $5 a square inch for 3 copies of the board that you're making. And there's links in the Discord. Thank you, folks, for linking to things. But yeah, I think it's really fun. It's really fun to, like, in the end up with something physical. Because I spend all my time in the software world. It's cool to have some things that I actually did. Hi, Paul. Hi, Redford. I did have a good break, although it was a pretty busy travel weekend. Another question. In terms of salary versus work joy, didn't Google meet your needs? Google should be a great workplace. It is. I was there almost 6 full years. And I worked on Google Maps, but the teams around Maps were changing, and the things that they wanted me to work on were things I wasn't particularly interested in. And I didn't like working kind of in the black hole that is Google, right? Like, you see me now, I'm like doing these streams. Like, that's not something I would be able to do if I was at Google. I can talk about like pretty much everything I know now, but when I'm at Google, it's kind of a like, you need to know all these really detailed things that I can't tell you in order to just understand what I'm working on. So it was time for me to look for something else, and Adafruit's been a wonderful place for me to be able to actually like work in the open and talk about the stuff we're doing and have a lot of influence over what we're doing and how we're doing it and all that stuff. So teach me PCB. Oh yeah, there's a class for it. Yeah, starting small is good. I do say KiCad, and I think the creator of KiCad says KiCad, but KiCad is also a popular pronunciation. Yeah, I learned a lot from watching Adafruit videos. That's part of the way that I got into working for Adafruit in the first place. Doctor asks, what do you feel is the most important thing you learned while at Google? That's a good question. I feel like the things that I came away with after being at Google were there are very few places that have that much code and that many users, right? Like, I in particular was working on the server that like serves up the map tile data. And so we were kind of a critical service that like a lot of people used. So seeing how they handle upgrades and changing things and just day-to-day maintenance is just something that you can't get everywhere. And then being in a large organization with a lot of code, you work in a team, so you have a lot of people around you who are more knowledgeable, and you learn from them. And you can also see like the policies that have been put in place to make like a lot of people working in the same code base sustainable and not too terrible. Keith E says, how did you start getting surface mount parts? It seems like a steep investment if you're just trying to start. I've kind of always done 0603 surface mount parts, and then when you design your PCB, you can do hand soldering footprints, and that generally just means that the pads on the PCB are larger, so it's easier to just use a soldering iron. I've thought about doing the toaster oven thing, but I've just, like, I tried to do my own, which was a mistake, but generally you can hand assemble a lot of stuff, even if it's surface mount. The one thing that's really hard to do surface mount the hard thing to surface mount with an iron is anything with a pad completely underneath. But it's actually like not that common. So I think people would be better off doing more surface mount than they think they can, because it's really not too bad. Of course, I have pretty good eyes and I'm pretty young, so I don't have like too many dexterity challenges. But generally, I think it's actually better. Yeah, and Flux is good. Flux is Flux is a compound, like a liquid that cleans the joint and makes solder flow smoother around the joint. Solder on its own won't kind of like flow. You need some flux. So even when you have a wire of solder, like it's got flux in it to make it move. But sometimes that flux in the wire is not enough, so you need like extra stuff. A asks, I can see a soldering station behind you. Did you learn to solder at the computer education? I did not. I kind of wish I did. It was definitely one of the hurdles that it took me some time to get over. The very first thing that I designed that I needed soldered was like some headers, and I like went to a makerspace and paid them to solder them for me. Soldering is not as hard as it can seem if you've not done it before. There are some really good tutorials. I know Collin's made some really good videos about soldering. It's good to start just with pin headers. So like pin headers are like here. So on something like this, hold on, let me change the camera mode. So this is a Pico, right? And if I were to get into soldering, like what I would start practicing with is just like pin headers. So like these are pin headers. And so there's little holes in the board that you'll get. And what you'll do is you'll use a breadboard to just sit the headers in and then have the board on it. So it won't move around. And then what you do is you kind of like put your iron like in the corner between, like, so that it's touching the pad and the pin. And then you'll touch that joint with the solder and it should like kind of suck into the joint if the temperature is right and stuff. If it doesn't kind of flow like that, then your temperature is probably too low. But pin headers are a great way to just get some practice with soldering. And then it gets kind of more detailed from there. But there are pretty good inexpensive soldering setups that you can start with. This one is not inexpensive. It's a bit fancier, but that won't matter until you have some practice. Dylan says, I thought I was terrible at soldering until I bought a better iron with temp control. Yeah. Should there be opportunities to learn soldering in a CPE degree? I don't know what you mean by CPE, computer engineering? I was kind of surprised that I didn't do it. Like, PCB design seems like fun and something we should have done in school. I took a couple electrical engineering classes, but didn't actually do PCB design. Starting with tacking the far corners of pin headers is really helpful too. Get the outside bits, then work to the middle of the line. Oh yeah, so a general rule for soldering is that the first solder joint you do for anything, that's the one that's gonna dictate the position. So if you're doing a whole line of pins, do one and make sure that it's lined up. Like it could be crooked, but if it's crooked, what I would do is just put your iron back, you'll melt the solder again and then make sure that it's straight. And then take the iron off, let the solder solidify, and then double check that it's in the position you want. That works for other surface mount things as well. So like always make sure that after the first joint you do for something, it's where you want it. But once you have it there on that first joint, then it's easier to to do that. And folks are pointing out that microscopes and like eyeglasses things can make it easier too. Who did you recommend watching regarding soldering? Didn't get that. So in the Adafruit channel, one of the other folks that works for Adafruit has done some soldering videos. So just look in the Adafruit, like just under Adafruit, look for soldering. There'll be good stuff there. Deshipu says, next week we're going to run a soldering workshop at the local university and also circuit Python programming. That's awesome. Oh yeah, SmartPants28 says, SMD is an art in itself. I've tried with dotstars, lol, nightmare for me. Yeah, so dotstars are definitely one of the more difficult things to solder, hand solder. Neopixels are kind of tricky too. They're definitely not the things I recommend starting with, largely because some surface mount things, like the pins will actually kind of like come out, and that means it's easier to like touch it with your iron. But if that's not true, in the case of like dotstars, you kind of have to like get it up against the side of the thing, and you can risk melting it. But even when I melted things, it tends to work still. So you'll figure it out. I think it's worth it. Don't be scared of it. Get yourself a $100 iron or less, and start from there. Just do it. Especially pin headers. Pin headers are really easy to start with. That'll get you used to like how the solder flows and stuff. Okay. So since we're talking about boards, why don't we start with that? So let me switch to the overhead and just show the board I designed. Did I talk about this before on the thing? I'm not sure. But let's get my headphones out of here. Switch to the overhead. Hopefully it's still working. It is, and I'll just, it's kind of out of range, but, ooh, it's warm. So here's the board that we're working on. So this is let me hit the lock button. Let's see what people are saying. You mentioned the board, but you hadn't received it yet. Thanks, DCD. Check with your local hackerspace. I'm sure they can run something. Yeah. My first SMD project used paste and regular iron. The paste made it easier. Yeah, so I think paste can actually be kind of hard because if you have to position the part, you might actually smear the paste more places. But if you are soldering something that has multiple joints, you can put the solder on the first spot before you put the part there, and there's like you can move the part onto there once it's liquid. So this is the Raspberry Pi CM4 IO board. It's just a little bit too big for how high I have it, but that's like there's a little bit of a power section here that we'll just have off screen. So this is the CM4. This is the CM4 Compute Module 4, right? So this is like all the stuff that is on a Raspberry Pi 4, but on a module. So there's connectors under here that sit down on this board, and then it breaks out all the things. So like here's the SD card that has all of the software on it. This is USB, and this is a USB device here. This is Ethernet, 2 HDMIs. And then this is like screens and camera connectors that I'm not using. But what is here is the normal 40-pin Raspberry Pi header. So I designed this board, and I have more copies of it that I haven't soldered together, that I haven't assembled. So what it is it's the 40-pin header, and basically it's wiring up all these connections. so that I don't have to do it every time. So there's a JTAG header, which is both JTAG and this SWD. It's the SWD form factor, but it's still JTAG wiring. It's just in the different thing. And then, so that's so that you can use a debugger to connect directly to the Raspberry Pi core. There's a STEMMA QT that I haven't tested yet. There's these 6 pins for the UART. So what you can do is I've got this, unplug it. I've got this USB to UART converter here, and I just have it so that the pinout matches exactly. So all I have to do, like there would be a USB cable plugged in here, but I can just plug that in, and now I've got my like debug UART output directly going to the USB, which is cool. And then what I did is, because I was debugging by blinking LEDs, I just added 4 LEDs to it. So these are 4 3mm round LEDs that you can buy off Adafruit, and these are 4 resistors. These are all 1K resistors. They're not that, you don't really, like 1K is kind of the highest value, I think. But these are in series with the LEDs. So LEDs won't restrict current on their own, so you need to have a resistor along the same kind of wire. So that's what these resistors are for. These are just the current limiting resistors for the LEDs. And then this header here is 5. It's a ground, and then it's the 4 lines that are also connected to the LED. So this is like if you want to use a Salier to like measure your blinks, you can do that. And then yeah, this is the Chickadee logo that I designed back when I was doing the flight controller stuff. I still like to put it on. Oh yeah. Lady Ada just asked me if she wanted to join the stream. So maybe she'll drop by later. Okay, so this is yeah, so this is the board I did. I haven't tested everything. I've been using it, so a lot of it does work. I haven't tested the I2C because I don't have I2C working yet, and I haven't actually tested the JTAG connector because it was too far away. I got like an extra length of cable by just using the SWD instead, which worked. So yeah, if you want to buy a copy of this and then assemble it yourself, you can get it off Oshpark right now. I think it's about $30. It's not super cheap because it's kind of a large board. Maybe it's not 30. Oh, you know what? I think it was 30 because I got it rush, but it's probably 15 if you're willing to wait a little bit longer. So I think I can let's just pull it up. I will switch in just a second. So here's my project history, and you can see like I have a lot of different boards that I was experimenting with, but I can copy this and also pull it up. Guest tease. Yeah, no promises. She just pinged me a message. It's been a while since we've had Lady on the show, so Lady Ada on the show. So I'll always take her up on it if she wants to. She probably wants to see how much progress I've made. Dexter says, could you use the board with Raspberry OS? Yes, you could. Yeah, so it's just like one particular pin out of the connector. I'm not sure. I think you can debug Linux. I think you can debug Linux even if it's running. I assume you can. I've just never done it. There is some like settings that you have to put in your config.txt to get the JTAG pins. Smarty Pants says, is Oshpark very expensive even with larger quantities? Oshpark has a medium service, but I tend to suggest like PCB Shopper. Like they have their 4-layer service, 6-layer service, and this bulk order. Volume discount for prototype, and 4-layer 40% price reduction. I think of them more as prototyping. There's also PCB Shopper, Adafruit.com I think is a pretty good like comparison shopping in terms of pricing. Here's another fun fact that I think, according to Drew, I'm the person that inspired this After Dark, the After Dark version of Oshpark. I think I can take credit for that. So if you look at I think my website's still up. Yeah, this is like, I'm not doing my drone stuff anymore. Do I even have, yeah, so here's a picture of one of my boards. This is kind of an ugly version. This is a 4-layer board, and it couldn't do the black FR4, or this is a weird version of the black FR4. Oh yes, but here you can see this style, which Oshpark now makes available as After Dark. What it is that the core fiberglass of the PCB is dyed black, and then the solder paste, or not the solder paste, solder mask on top is clear. And so you can see the copper of all the traces on the board. And then the places that don't have the solder mask end up getting plated gold. The only way Lydia knows what you've been up to is to watch your streams. I mean, we do have internal meetings, but we have a CircuitPython meeting on Monday that I missed because I was out on Monday. I think there are config settings to boot in a debug mode for most distros. Yeah, I don't know. I haven't tried using it with Linux stuff, but there's no reason there's nothing fundamental about the thing. Like the pinout for the I2C, for example, is the same. So it should just work, but I haven't tried it. Okay. So that's the board. I think I've made a lot of progress. It's been 2 weeks, and I've been pretty like sucked into this, which is bad for the Bluetooth stuff, but good for my productivity. SmartyPamp says, is troubleshooting the 4-layer board difficult? For example, if there's issues with the tracing. Generally with a 4-layer board, what you'll do is the 2 inner layers you'll use for power only, which means that your signals are still on the outside. So if you have to do something to the signals, you still can. I did have a bit of an issue with one of my designs when I was doing the drone stuff, where I had updated all of the copper layers, but where the drills wasn't updated, and so I ended up like connecting 2 parts that I shouldn't have. So yeah, that was not good. But yeah, so there's this repo here. I don't know if I've shown this. So did I talk about this peripheral stuff? So we have this samd-peripherals repo that we did kind of a while back when we added the samd-51 support. This is meant to be like a little bit of an abstraction above the registers that is not specific to CircuitPython, but still like kind of helpful. And CircuitPython uses it. So I started working on the same thing here for the Broadcom chips for the Raspberry Pi. So if you go to this URL that I'll just dump in the chats. So what this is going to be is my goal with this is to this is all the stuff to get you to where you would be with like a Cortex-M, like very basic firmware. So it should boot everything for you. It should set up all the interrupts. So the way that interrupts work, and this is what I've been working on, so my brain's there. But in Cortex-M, generally the way the interrupts work is all you have to do is define a function called interrupt name underscore handler, and it takes no arguments, and then that gets called when an interrupt happens. And the way that that works is there's some code in the startup stuff that calls those functions with those names based on what interrupt happened. And there's a default implementation, which in GCC you can mark as weak, which basically says like only use this version if no other version exists. So you provide a weak version of it that does nothing, and then when you want to use it in your like actual code that you're working on, you just define it again, but don't mark it weak, and that will kind of override the other one. So this is kind of like meant to do all this convenient stuff. One thing that I've been working on a lot is there are these SVD files, and what these do is they describe the memory map of everything in a Cortex-M system on a chip usually. So maybe it's worth just talking. Let's just pull up the SAMD datasheet, because we showed this chart before. But let's just take a weak interrupt handlers. That's pretty cool. Yeah. Let's just recap briefly like what system on chips are. And we'll do that by looking at the data sheet here. So this is for the SAMD-21. So this is what I started working on for Adafruit. It's much simpler, much simpler than a lot of other chips, so I'd like to start with it. So this is just to get, this is not for the Raspberry Pi specifically, but this is to get you in the mindset. So this is kind of why they're called SoCs, or system on a chip. There's a CPU, and then there's a whole lot of other stuff. So think of, if you've ever made a desktop computer, right? You plunked the CPU in. That's kind of like, they're system on chips too, but they're largely just CPUs. So you can think of that as one bit. And then there's like NVM, which is non-volatile memory. So this is like your hard drive, right? And then you have RAM, like your RAM sticks. But all of this is incorporated in microcontrollers and some microprocessors, kind of all on one chip. And in fact, like the Raspberry Pi, these two things are not on the same chip, right? Like you actually have the equivalent of NVM for the Raspberry Pi is your SD card, and then you actually have RAM, a separate RAM chip, external to the CPU, or external to the main chip. And then there's this bus, and then there's all these different peripherals. And I really like to emphasize that people think of these just like you would think about a temperature sensor on an I2C bus. This is another piece of electronics that is running separately from your CPU. They might actually be synchronized in the sense that they're using the same clock signal, but reality is that they're like relatively independent. What's the main difference between a .svd versus, say, a flash.xml? I don't know what flash.xml is, so I'd be curious to know. SVD is an ARM thing specifically, and it covers kind of all of these things. So maybe I should just pull up the SVD for a SAMD-21 too. So what we can see here is there's this like high-speed bus matrix. So this is like the way that the CPU talks to a bunch of other stuff. Generally the way that you talk over this is it's called memory mapped IO. So each of these individual peripherals will have registers that are sets of state that cause the peripheral to do something. And the way that you read and write to those is through memory mapped IO. And so what you get is that you have this chip that has a CPU and RAM and like other memory mapped IOs for peripherals. And so you can see that through, is it product mapping? Yeah. So this is the memory space. So it's this SAMD-21 is a 32-bit system, so you have between 0 and like all Fs. And you can see that like at the very highest level, they've kind of split things into chunks. So for example, like here's the chunk where RAM is, it starts with a 2, and all the peripherals registers are memory mapped starting at 4. And then this shows us, okay, starting at the 4, now we have these 3 bridges here, bridge A, bridge B, and bridge C, which if we go back to the block diagram, we can see here, here's light blue is bridge A, green is bridge B, and bridge C is this like more robin's egg blue. So there's like some like control here at this level that's like looking at those couple bits in the address and deciding between these three things. So that's there. And then now we can see that they tell us exactly the memory locations. So for like, if we're looking at bridge C and Circom, which is what does I2C and SPI, like you can see Circom 0 is at this address, for example. So what an SVD file can do is it can kind of explain that in a programmatic way that you can then use. And there's kind of two ways that it's used. It's used, it's super useful for debugging. So it allows you to like browse all of the state of the registers. And then it can also be used to generate C code and C data structures like structs. So by having an SVD file to kind of explain all this stuff, it will explain not only where everything is, but like all the individual registers and what the values mean as well. So maybe let's just, let me get my Raspberry Pi back going. I wonder if I can, you know what, I could probably do it under the, I can probably actually do it under the overhead. So let me just show that. And maybe I'll just back it up a little bit. Okay, so how do I have this set up? I had HDMI set up because I do have a display on my desk here, but I'm not using it at all, so we don't really need it. I have all these wires I'm untangling. So first up, I've got power. So I have it on a switch so I can turn it off and on. So I will just plug it in, the switch is off. And then the only other thing I need is, because I'm going to debug it, I have a J-Link on my desk and ooh, I can barely reach. So this is going to the J-Link here, and I'll just plug it in to the SWD. Oh, and I also was doing the USB UART. And so I will plug that in like that. So this is my debugging setup. And let me do desktop with overhead. So here what we have is, this is my fancy terminal setup that I've got going. And so what do I have here? So this left window I'm using for two things. I'm using it for running OpenOCD, which is the thing that interfaces with the chip itself and then provides like a standard API that GDB can talk to. In the right-hand corner is GDB. So this is where I can inspect stuff. And then this is the UART output here. So you can see that because I was showing you, it disconnected and now reconnected. So I already have the micro SD card in. So let's get it started and we'll see it start up. And it takes a little while, but we can see we got the debug print output. And now what we can do is we can do this OpenOCD command, and it successfully like connected to the CPU core. And now we can control it. So I've actually been doing it a little bit before. I'll just reconnect. And so now it's telling me where I'm at. I'm in this, it's checking to see if USB is initialized. And I've already loaded this thing that is awesome, and anybody who does GDB stuff should take a look at it. So there is, it's called PyCortexMDebug. So you can actually run Python, like Python is built into GDB. So what you can do is you can like hook into GDB and like do extra stuff with Python. So when you run a command, it calls some Python code that does some stuff. which is super powerful. So there's this bnahil PyCortexMDebug thing. And what it does is it reads SVD files and then makes it easier to browse the register state. And I'll show you what I mean. So I already did this SVD. You can do SVD load, which I already did, and I have an alias for called SVD BCM. I'll just do it again. You can see that this is the Broadcom peripherals repo inside of TinyUSB. And in there, you can generate a BCM 2711 LPA.svd. So that's an SVD file that has the data for all the peripherals as if when they're in the low peripheral address mode. Cortex-A's get more complicated because from the CPU you can move around the registers and the memory and stuff. But for now, this is kind of for the one-to-one mapping of that. And that's, I think, probably the last thing we talked about, because I remember we got it working at the end of the last stream. So what I can do now is, now that I've loaded the SVD info, I can just type SVD. And now we can start taking a look at some of the stuff that I've already defined. So there's this vcmailbox thing. This is how the CPU code talks to the GPU code on the Raspberry Pi. And that's important because power stuff, for example, turning on the USB power to the USB peripheral is controlled from the GPU. So that's one example. So we can do SVD vcmailbox. And now we can take a look at like all of the registers and their state for the particular thing. And if you do the /x, it'll do it as hex rather than as decimal. So we can go back to SVD and we can start to see the things that I've defined. I had this GPIO one, we have a UART 0, we have the LIC, which is just this legacy interrupt controller that I'll add more to later. Right now it's really basic. And then GIC is this generic interrupt controller. This is a new thing for the Pi 4 and where I'm like really looking at right now because it's how you get interrupts, which is the thing I'm working on. But then you can see there's like 3 different USB things, and then there's also more UARTs. So we could just say like UART 5, and we can see all the registers. And I actually copied this. This is a standard UART from ARM. And so I just found another microcontroller that actually had the same UART. So I just copied all of that. Those definitions there. I wasn't able to do this for the generic interrupt controller, so I've done more work on that myself. So if we just look at the GIC dist, this is the distributor part of the, actually let's make it wider. This is the distributor part of the interrupt controller. And I do have it, I have a lot of tabs open. So it is publicly documented in a couple ways. There's the specific controller I have open here. So this is the ARM documentation for the GIC 400, and it will tell you like what all the registers are. So you can see that like here's the names of the registers, the description, whether they're read-only, read-write, and what the offsets are. So I took all this stuff and I copied it and moved it into the SVD file so that what I can do is I can just use this PyCortexMDebug thing to print out the value of all the registers. And then what I can do is here like, oh, this register has something besides non-zero. So this is the status register. And so I can do something like this. And now I can see that for these interrupts, I can see whether they're active or not. So the USB interrupt is active, multicore sync 3 is active, and nothing else is active. So I had to do a non-trivial amount of work to just get that listed. And then a lot of these peripherals actually have registers that just have fixed values as IDs. And so that's what these PIDR and CIDR registers are is that I set it up so that they know what the value should be, and they can tell you that it's valid. Cordy asks, what tiling manager are you using? I'm just using console, and it's just the console stuff. I'm not using like a separate tiling manager at all. It's just like the terminal on KDE. And then there's also these clusters. So I did these as clusters because there's a lot of state that you maintain for every incoming interrupt. So maybe I should talk more broadly about what interrupts are, since I'm getting into the weeds. So let's pull up the BCM ARM peripherals thing. And this is the obviously I had this graphic pulled up. It's really helpful. So if you've ever done like an I2C sensor, it's not uncommon to see an IRQ line for that. And that's just it's an individual pin that just says, when this pin is low, there's some reason that we wanted to interrupt you, and we wanted to let you know that the thing that you wanted to know when happened did happen. And that's like the most generic kind of way to talk about interrupts, is like their intention is to actually stop what the CPU is doing and have the CPU do something else. And how quickly that happens and at what priority and blah, blah, blah is complicated. But the idea just being that, like, if this thing goes low, then we want an interrupt, and we want the CPU to say, like, oh, I got to go do this thing for a little while, and then I'll go back to what I was doing. And so all of the peripherals on the chip and have these wires, in this case they're all wires, that are running to this like central place that's managing which one of these wires we actually want to pay attention to and at what priority and things like that. So it gives them these IDs. So like the VC peripheral IRQs are all between IDs 96 and 159. And they're defined here. So here's all of the video core interrupts. And you can see what they are. And so I listed all these out in that repo, for example. So if you don't have to copy this now, there's a Python file that has a list of all this stuff. But that's what then generates the SVD file that says, like, this particular register for interrupts is for this particular interrupt on this chip, which is really handy for just debugging to see, like, oh, how far is the USB interrupt getting? Because the highest of my goals right now is to get the USB examples working from TinyUSB. And in order to do that, I have to get USB working. I have to get USB interrupts working. So like the host computer will send a thing, and that will trigger the CPU to be like, hey, like the host computer is asking you something, like we've got to do some of this. So yeah, interrupts are a way for external kind of devices, like peripherals, to let the CPU know that something happened. So it's up to the CPU to say, like, I care when this thing happened. And there's kind of like all these stages along that way to like tell things that you care about it. So like the peripheral itself has to say that, has to know that you care, and then that will basically cause the signal to leave the peripheral, and then that will go somewhere else, and you have to like tell it as well that you care about it. And then generally there's a switch as well. So yeah, interrupt request, IRQ. One thing that threw me off when I first looked at this is that there's PPI and SPI. I was like, okay, great. We need SPI as an acronym in this case, because that wouldn't be confusing to anyone at all. It's an ARM, from what I can tell, it's an ARM terminology thing. So PPI is a private peripheral interrupt. I think the middle P is peripheral. And the private means that it's specific to the individual CPU core. So one thing that's more complicated about the Raspberry Pi chips is, or these Broadcom chips, is that they have multiple CPU cores. Up until now, all of the things, well, that's not true. The RP2040 has 2 cores, but we only use one of them. And it's got 2 copies of the interrupt stuff. But basically, if you have more than 1 core, you have to worry about who's going to handle an interrupt. And so that's added complexity here. So these private peripheral interrupts are interrupts that are specific to a single core. They're kind of like independently done. Whereas this SPI is shared peripheral interrupt, meaning that once one core handles it, the other cores won't see it as pending anymore. So generally what happens is that a signal from the peripheral comes in, and the controller, the interrupt controller says, okay, that's pending. I see that that interrupt's coming. And then it goes from pending to active when the CPU is actually working on the interrupt, actually responding to it. And then after it's finished, it can either go to active again, or it could be pending again. Or it could be inactive, or it could be pending. Because it's possible that as you were handling an interrupt, the interrupt came in again. And so that would be like a case where it's both you're working on it and it happened again. So when you stop working on it the first time, it's still pending the second time. So yeah, it's kind of complicated. Interrupts are kind of complicated. But this is something that it's interesting because CircuitPython doesn't expose this directly to user code, and this is something that we've heard time and time again that people want. But one thing you want to make sure of is that if you're in an interrupt, lower priority interrupts don't get handled. There's a notion of like what is the highest priority. And so you always want to make sure that your interrupt handlers are really fast. So that both you can get back to the work that you were doing and other interrupts can be handled. Keith says, do you think the existence of shared peripheral interrupts being something you need to address here will drive more multiprocessing focused work in CircuitPython core? Or is this enough of a subset of kinds of tasks that you can address this is without needing to solve multiprocessing? I don't think we need to solve multiprocessing at this point. I think that we can just treat it as like we're only going to route stuff to the first core. And in fact, I started actually writing some code that turns on and interrupts, and I made it turn, if you call enable interrupt, it will automatically say enable it for the core that called it. So yeah, I'm not getting into multi-core stuff yet. It's just, it's going to be a lot of work. It's really interesting for me to learn how cross-core stuff is managed, though. So like this, one thing that I haven't seen in so the interrupt controller on the Cortex-M stuff is typically the nested vector interrupt controller, the NVIC. And I haven't seen it having software-generated interrupts, but this does. So the GIC 400 has software-generated interrupts. So you could have one core write a register on the interrupt controller saying, turn on this interrupt, this numbered software interrupt, and then you could have another core get interrupted as a result of that, which is pretty neat. There's all sorts of different ways of talking between cores. Smarty Pants says, do you need to set up delays for interrupts? No. I don't think we have any sort of delays that we need to do. One of the tricky things, as far as I can tell, I haven't gotten this working yet, so it's not entirely sure that it's right, but one thing that the interrupt controller on the Cortex-Ms, the NVIC, will do is it will automatically kind of store all of the register state for you and then call it into your code and then restore all of the register state after. But that's not the case, I don't think, for these Cortex-A level stuff. So there's some initial code that I copied from one of the OS tutorials for Raspberry Pi that just like stores all the register state. So, you know, one of the delays that happens with registers is just what's called context switching. Like you're storing all the relevant state before you change it and then restoring it after you're done. It's called kind of a context switch, and that can take time. Good night, doctor. Thanks for hanging out. Yeah, it's just the sun's going to go down earlier and earlier, so yeah. Okay, so what do I have? I'm assuming at some point we'll chat with Lady Ada, but before then, I mean, she might have other stuff come up too. So I've done a lot of work on the SVD file, which is really helpful for debugging. It also generates a giant header file. So let's just show that. So it's this I'm calling it Broadcom gen and then the header file. It's just this giant file that's actually generated with a program from ARM. Oh, Benjamin's asking, can you even have delays inside of an interrupt? You can, but you generally don't want to because if you have delays inside of an interrupt, you're blocking everything lower priority from running, right? So if you get that interrupt again, for example, it won't be handled. It'll be ignored. So like the interrupt controller, if an interrupt happens multiple times, but you don't service it, it just knows it happened once. So there's a risk that you lose resolution on your interrupts. But then also like interrupts have priority. So if you're doing something high priority and you delay, nothing else can happen. Including like the code that's not in an interrupt at all won't run either. And this is like the basic microcontroller model of the world. There's like more complicated things you could do with interrupts as well. So here's the generated file. This is generated by SVDcon that you can get from the SimSys repository for ARM. One thing it does is it pulls out all of the interrupt numbers, which is quite cool. And in fact, what I didn't say yet is that I'm actually using Jinja. So Jinja is a Python templating system. So instead of having one big long SVD file all written, I use Python to generate the final one. So here's the top level of it. It's got the top level information about what board it is, but then it uses Jinja macros to fill in all of the individual peripherals. So in order to have like your 2 and 3 and 4 and 5, I'm actually there's a SVD thing for saying it's derived from something else. But this is how I'm like this is how I'm like piecing it all together. So for an individual thing, I've got this like, okay, here's the GPIO.svd.jinja thing. So to instantiate it, you give it the name that you actually want and the base address. So this should make it easy to generate different SVD files for different like static memory layouts that you want to do. Bruce says, I've had very small delays in interrupt routines where we had some hardware issues, but not normally done, as Scott said. Yeah, generally you want to do it pretty quickly. So for example, the USB interrupt, what it does is it generally just adds an event to a queue that then gets processed later. So the only thing that's really happening during the interrupt is just like queuing up some more work that'll be done outside the interrupt. So here, for example, this is not view. I'm abusing, there's a Jinja HTML syntax that makes it easier to see. So this is, you can see here's the macro. So if it's curly brace %, then it's like it's a control flow thing. If it's just 2 curly braces, it's kind of just like replace this area. So you can see here that I'm like taking the base address, formatting it, and then replacing it there. I'm putting in the interrupts, and I have the interrupt offset set. So this is the offset like into the VC range of interrupts. And And then I'm using, like, you can do, in Jinja, you can do for loops and stuff. So I also have, I did a lot of work for the GPIO so that there's a thing called alternate functions, which is like what thing inside the SoC is actually controlling the output. And so I have it generating like nice names for all the different alternate functions as well. So yeah, individual files here for the different peripherals, and then a top level one that kind of brings it all together. And then when you generate it, you get this giant SVD file, which is this, and it's, I don't know, 40,000 lines long, something like that. And this is like individual fields within a register and description and how big it is, and all that stuff goes in here. So it's a giant file that's not very fun to do. And then what you can do from there is you can generate this thing, a nice lightweight summary, hopefully. So one thing it does is it creates this enum of all the interrupt numbers, which is really handy. So if you wanted to just reference the your interrupt, you could just say UART IRQN. And then it does all of these, that's some boilerplate, but it does all of these giant structs. So like this is a single register, and this register has this many fields. And so it generates all of these C structs. It allows you to say like peripheral, arrow, register, dot, something, and you can like set a particular bit, or you can read the whole thing. And that's just like a lot of that. Somewhere in here. So it has all of the base addresses for everything, and then it casts those addresses to the struct types that represent them. So you can, in your C code, you could do just like GPIO, arrow, and that's how you're like interacting with this struct type. And then lastly, you also get like all of these bit masks of like exactly what position and mask like all of this data in a particular register is. Just a lot of boilerplate generated code. There's some more enums, just like tons of stuff, like 17,000 lines. But yeah, all meant to like both make it easy to interact with registers from C, but also to use the SVD thing in GDB to understand like the state of everything. So that's all the SVD work. Now I did the GPIO alternate function stuff. I brought in the USB stuff and like had to reorganize it some. And now I'm trying to get the interrupts working. I think so. I got to the point where if we see like here, we can see these three init statements are initialization statements from TinyUSB. And then if we look where we are here, we're actually past the initialization of the USB peripheral. So we got memory mapping working, and then the next step was to get the it was trying to reset the USB device, and that wasn't working. And the reason that wasn't working is because it wasn't powered on. And so I had to do the vcmailbox stuff. So I have a quick function I did in here called get power state and set power state. So you can say like, hey, set the USB device to on, and the USB device is defined in this generated file, which I have another Python script to do to generate this stuff from. So yeah, so I think I'm correctly starting the USB device, but I don't have the interrupts coming from it yet, so it won't really be able to make any progress because it won't be able to tell us like, hey, time to like something happened, take a look. And so the next step is to get into the interrupt handler. And how does that work? Well, in assembly, so here's all the startup code. This is the loading the vector table. So the vector table is if these exceptions happen, call those functions. BSS is the 0 place, and then we go to main. So this is what I was talking about, saving state during an interrupt. So there's this macro called IRQ enter. So it saves all of the register states to the stack. Exit does the reverse. It loads it off the stack and then returns. And we have this exception vector thing, which I should actually check. This EL1 IRQ. Yeah, so that should be... I don't know what the difference between EL1T and EL1H is. I should double check this. Although all of these things that are set up are alias to this handle invalid entry. So this is how we were like debugging. I was debugging some crashes. Is that it ends up in this invalid entry, because this invalid entry, it saves some state to registers after doing the initial thing, and then it just hangs. And that was working. Hi, G3 Holiday. Yeah, so I think these vectors are set up correctly because we were having some synchronous faults come in here. Those are the things that, like, if you read the wrong memory or set something up wrong, or like something errors out, it's the equivalent of like a hard fault handler in Cortex M world, where like you tried to divide by 0 or load 0 and things like that. So this should work, I think, but it doesn't. So so this is the top level table that the CPU looks at when an exception happens. These are different types of exceptions that happen. One of them is the IRQ exception, which then should go to this branch and link to handle IRQ, which is in here. It's also weak, which, I mean, maybe there's a small chance we have a separate handle IRQ. Like that looks right because it's got our break in it. So I don't think that's wrong either. But basically once we could get to this handle IRQ, we can then read from the interrupt controller, hey, what interrupt caused me? And then we can call out to the one. Ah, H is for handler, T is for thread. Thank you, Andrew. Is for thread. Huh. Should work, but doesn't. I know, right? I mean, the MMU thing was just the access bit. Like, yeah, so it's just figuring out like exactly how the bits should be. So basically what I'm trying to do is I'm trying to get here, and then I'll hit a breakpoint just to show that I managed to get there. So what I was doing before I took a break before the stream and had lunch was trying to use the SVD to make sure that I set all the bits I thought I should have. So what I didn't check was the USB. OTG global. So if we look here, there's this interrupt register. So, I mean, I assume that That's interrupt mask. So it like interrupts start from, oh yeah, there we go. This is what is interesting. So generally what will happen is that there's a lot of signals in the peripheral itself, and then it masks which ones it should pay attention to. And then if any of the ones that it wants to pay attention to are set, then it will have one line go out of the peripheral to the interrupt controller. So by reading this register, I can see which of the internal signals to the peripheral actually caused it. So that's that. I don't know this register mapping very well. There is a device version that we could look at too. Oh. It's not working quite right. So it has control and status. Oh, it does have interrupts as well. Each endpoint interrupt register and register mask. So like each USB endpoint has interrupts as well. I don't think I should be. I don't think I should have to manage this. I'm hoping that USB will just manage. TinyUSB will manage it for me, because this is an existing peripheral that it's already works on STM chips that have the same peripheral. So the next thing kind of down the line is the interrupt controller, and that's specifically the distributor. So if we look here, and then we look at the interrupt line, like we did a little bit earlier, we can see here that like USB is active. So it is, the peripheral is saying I'm active. Assuming one thing I should maybe triple check is that this number is correct, like this mapping is correct. I mean, I believe it. I believe that USB is active, but it's possible that like I'm not correctly designating these things, which is possible, but I don't know. So that's one thing to check. There's another thing to check, which is just the control register. Like, is it on at all? That's not right. CTLR. So like group 1, group 0 interrupts are set. If I try to look at the group, so these are clusters, so there's just a lot of them. And I'm not sure what group it's in. Maybe it's in 2. But I do have it mapped. All right. We might have a Lady Ada here shortly. Let's look at 3. USB group 0. Should be fine. Everything's just group 0. And then we can check if it's enabled. Which I think it is. Yeah, USB is enabled there. So it goes from the distributor and then it goes out to the CPU interface. I don't know. It doesn't work. It shouldn't be active, but it should be pending. We can check that. Oh. Doo-doo. Oh yeah, you probably won't be able to see me. I cannot hear you. Are you muted? Did I mute you? I'm seeing a... It's worked before. I still see the mute icon next to you. I don't know why that is. Can't unmute. Huh. Oh no. We could try it on Slack. we could have Lady Ada do maker charades. Does it show you as muted? Okay. I'm not marked as streaming. Oh yeah, try Chrome. I'm not reading the Discord chat quite yet. Let me see. We're doing a role play at the start of every meeting.
Okay, I think this is fine now.
Yeah, I can hear you now.
Weird Firefox is like, it's like you have a mic, it sees the mic, but it's still not working.
Still doesn't work, yeah.
All right, well, what's going on? What are you doing?
I'm trying to get interrupts working.
On the Cortex M8, A8?
On the BCM 2711.
What's working so far?
Let's see. This whole saga. I had to get the toolchain going. So using the Arch version of GCC. And then I wanted to use the standard library, which is compiled for unaligned accesses. In order to support that, I had to get the MMU set up. Because once the MMU is set up, or by default, the MMU is set up so that you treat everything like a register, which means that any unaligned accesses it doesn't like. So we got that working 2 weeks ago on the stream. There was a bit that I needed to set that I didn't realize I needed to set, and then it worked, which is pretty awesome. So it just maps the virtual addresses straight over to the physical addresses, which is, of course, a new topic coming from the world of Cortex-M, where they don't have virtual memory.
Address is address. You want to read address 8?
Right?
We'll let you. Go for it. Go to town.
Yeah. So getting the MMU going was good, and then once I could do that, I could get string length working, which meant I could do print debugging out a UART, because I could measure how long the strings were. And so that's working. I have that debug working. And then I can blink LEDs with that too. And I felt pretty good once.
Nice.
I felt pretty good once I got that. And so I kind of stepped back and did the Broadcom peripherals repo, which now has an SVD file, which allows you to do header files and some GDB integrations, which was really nice. So I was showing that in the stream earlier today. And TinyUSB, so the whole, I'm trying to get the TinyUSB CDC mass storage example going. And the next hurdle for that was that TinyUSB was trying to reset the USB peripheral, but it was never coming out of reset. You'd write the 1 to the bit and then it would never get cleared because it was never resetting. And so I had to add support for the video core mailbox, which is like telling the GPU like, hey, do this thing for me, meaning turning on the power to the USB peripheral. And then once I did that, it got all the way through all of the init stuff. And so now that the point I'm at now is it's just looping, seeing like if the USB is connected. And so I know that I'll have to hook up interrupts from the USB peripheral. So that's what I've been working on. And like fingers crossed, once interrupts work, we can actually start to see stuff over USB.
Is there any examples out there from, low-level code that you can reuse, or is it you're kind of on your own?
I've been picking
manual.
I've been picking stuff up here and there. There are some like relatively good tutorials for like, oh, you want to make an OS by yourself on Raspberry Pi. Here's kind of how you do it. I don't think a lot of those are coming from the like microcontroller world like I am. So like I really do want to treat it like a micro, and like they don't necessarily do all the legwork to do that.
Yeah.
So that's largely what this whole Broadcom peripherals repo is for, is to like really treat it like to lay all the foundation so you can treat it like a Cortex-M. So I was talking about like, how in Cortex-M usually to do an interrupt, you like define the handler for it and then it just gets called. So like trying to figure out like I have to write the code to like do that in the peripheral thing, and then we'll be able to just say USB handler calls the TinyUSB handler thing, and off and away it goes, hopefully.
All right, cool.
Yeah, so I mean it's been like slow and steady progress on this stuff. Like I've been letting you know, like I'm not hitting too many walls. I'm just hitting a lot of hurdles that I am getting over.
Yeah, you just have to you have to do all the implementation.
Yeah, and like a lot of reading and a lot of learning about like how just like the complexities that come with like there's 4 cores.
Yeah.
And like what do interrupts mean in a world where you have multiple cores that can do those interrupts and things like that. So it's been a lot of fun, and I'm still digging through it and trying to get that stuff. 2231 Puppy is asking about low-level devel on YouTube. I did see that. I'm trying to do a bit more software engineering than a lot of the tutorials have. So like once I get interrupts going, like I'm hoping interrupts work for everything. Whereas like some tutorials might just have like one simple piece of the bigger puzzle. But yeah, how are you?
Good. Just finished up the state of the fruit. I'm going to test out Kepler's camera code, and I just have a ton of email to do. So I'm kind of in email land.
So you're like, let me go on Scott's stream instead, so I don't have to do all my email.
Well, I have to take a break because my brain starts getting frazzled, because it's like
right.
I do email for like 45 minutes, and I'm like, I need a break. But I thought I would just check in. I wanted to see. I haven't been in for so long. I was like, I should. So yeah, I do have to go because it's dinner time. But I did want to come by and I was like, you're doing this thing. And I was like, where are you? I don't know. I should go check it out.
Yeah, they were. Earlier when I said you would stop by, people were like, is that how Lady Ada knows what you're working on? Is just by watching your stream? And it was like, yeah, basically.
Well, that and the weekly meetings. And I look at the commits and everything. I see every commit that goes by. So I kind of know what people are working on.
Right. Yeah, and I think I've been pretty good about pushing to that Broadcom peripherals repo now.
Yeah.
I don't want to lose the work. That's part of it.
Yeah, for sure. I mean, like that's another thing. It's like, how do you make a tool? The whole workflow tool chain for deploying to this kind of chip. It's a lot different than a microcontroller, which is just super nice.
Yeah, I'd like to do like get in the Raspberry Pi imager at some point, which would be pretty neat.
Yeah, I think it'd be interesting. I mean, I think another thing is, there's probably other people who are interested in, working on that low-level Raspberry Pi stuff. I don't know if in the Pi forums people have chatted about it, and because it's like the peripherals library is useful for multiple things.
Yeah, there's some pretty good resources there, and one of the reasons I wanted to go kind of the SVD route as well is because I know the Rust people do a lot of tooling on top of SVD files. So like all the Rust embedded people, like they automatically generate like a bunch of Rust code based on that stuff. So I was like, this will be helpful for more than just me if we have these SVD files.
Totally. Yeah. I think that's part of what you're learning, right? Every time it's a new platform, you're like exposed to it's like they made decisions and they made decisions for a good reason.
Right.
You just have to figure out and figure out why did they make those decisions. I think that's something that, you know, you're really good at. You're never like, oh, they did something and it's stupid. You're like, they did something and there's a reason for it. I just have to figure out why are they doing it, and then I can analyze how to interface with like their decision process. Like it's all engineering is about trade-offs, and so I think you know the hardest part of engineering is being able to put yourself in the mind of the other engineer and be like, okay, well, why did they do this?
Right.
It could be that the code could be different or the design could be improved, but there's probably a reason. So like, what is that? You know, documentation tells you what it does, but not always why it does.
Well, I mean, that's what's so nice about us working in the open on all the Adafruit stuff is that a lot of those decisions happen in the public and people can see the reasoning behind it and see how things have evolved. And that's not a luxury we have with stuff that gets thrown over the wall occasionally from these vendors.
Yeah, like, yeah, I mean, we can ask vendors to do stuff, but if it's a binary blob, we don't, you know, we know we've asked vendors like, hey, we think you're not setting this flag, but like, there's no way to know. It's definitely, you know, I think it's interesting that, you know, people talk about security in, you know, firmware and stuff like, oh, I don't want to release my code. But then, you know, eventually you're running your code on a Linux computer where it's like, you can't secure a Linux computer. Like, not really. You know, you can always mount the file system. You can always get the executables and files off.
Right. Right. Yeah.
Physical you may not get the code, but you have physical access. So, which is kind of interesting. Somebody was asking me about that. It was like, oh, you know, you can't secure MicroPython or CircuitPython. I'm like, there's no such thing as file security. You should be using an external chip for authentication. Right. You know. Anyways, beyond the topic, but I do have to go. I just wanted to drop in and say hi and say hi to everybody. Thanks everybody for dropping in. And sorry, I'm in and out, but I do have to.
Have a great weekend.
All right, thanks, and everybody enjoy your weekend and a long weekend too if you're having it. Bye.
Oh yeah. Bye. All right. Timonsku asks, what are SVD files? It's a system view description. It's a thing that Cortex-Ms usually have, which tells you like what peripherals and registers there are and where they are in the memory map. They're super handy. I went into it earlier, so I'm not going to go into depth now, but they describe all of the register or the memory addresses and stuff. I've been looking at the Linux code for USB. I'm surprised that they don't have like SVD style stuff. As far as I can tell, Linux only really has the device tree stuff, which is like kind of higher level than that, than SVD. SVD covers like each bit of a register, which is really, really handy, but device tree does not. Device tree will tell you where things are, but it won't tell you the lowest levels of things. The unique way that ECOS operating system handled it. They're doing something. Protobuf descriptions files for peripherals. Yeah, I can show you it here. Like, so this is like this Broadcom peripheral, and if we just scroll down, there's like, it's all XML, which, you know, whatever. But you can say like, oh, here's a peripheral, we're calling it vcmailbox, here's a description, here's the base address, here's how many addresses it is, and then here's a register, it's called read, here's a description, the offset, and like access for it. If it has fields, you can say like how big the fields are and stuff. You can also say like what C types match up with stuff too. But I haven't done that. But yeah, it's incredibly handy, and you can generate like C structs and stuff off that too. There's an unhappy kid outside the window. But yeah, it's this giant file of like all the bits, and you can have enum values and things like that too, so that things get better formatted too. And you can derive from other ones. So if you have like multiple copies of the same thing, you don't have to have copies of all the registers. And yeah, there's an ARM provided thing called SVDcon that will generate a giant header file for you that looks like this. So it has like all of the interrupt numbers. There are more, I just haven't defined them all. And then it defines these giant structs that have like all the bit names and register names and things like that. So yeah, they're super handy. They're really, really handy. And I'm using Jinja on top of it so that I can move things around and like put files together instead of having to have one giant one to maintain. So yeah, that's all in the Adafruit github.com/Adafruit/Broadcom-peripherals is where you can follow along as I add stuff there. There's certainly more to add. I will add it as I need it. Oh yeah, and the other thing, Timon, is that you can use this Python extension to GDB to actually print out the register states. And like have nice names for the different bits and all that stuff. So here we can see like this is the pending state of all the interrupts based on the name of the interrupt rather than just like the number, which is really handy. So USB, right, so we've got 20 minutes. If you have questions, feel free to ask them. I was checking all of the settings along the way. So the distributor, I should show this. I have a graphic. It doesn't show here, although there is there's actually two different interrupt controllers in the Raspberry Pi 4 chip in the BCM2711. There's the legacy one and the regular one and the generic one. The generic one is one from ARM. And you can actually select between the two. And I'm not sure what bit checks that out. I thought by default on the Raspberry Pi 4, it's the GIC by default. So that should be set up. It's possible that something else is changing the state of it. So that's one thing we could check. Huh. Delay deferred service routines. Huh. So I do have to add these registers to the IRQ to the brain words. Add them to the SVD file at some point to make these easier to check. It's pending. Where is? I have too many tabs. So I think here, so this is the information for the GIC version 2 spec. So like the GIC 400 is the specific instance, and then the spec is the V2. Thanks, Unexpected Maker. Have a good one. This is the... That's not it. Introduction. Where's the... There's a diagram. This is all words. I don't want words. I have too many tabs open. What is this? Oh, this is the UART documentation. that's the ARM core docs. I wonder if it's in here. Can I make this big enough that it will give me the sidebar? Introduction. Ugh. Probably like, there we go. I was right on the cusp. This is not what I want though. I found a good diagram, but basically, so the so this is not where there's a good diagram and it's not in this doc. So there's different pieces to the generic interrupt controller. There's the distributor, which manages all the incoming signals and then forwards those signals into specific CPU interfaces. And it says that there's one for each processor. This virtual stuff we're going to ignore because we're not doing virtual machines. But the distributor is just kind of global settings amongst all the CPUs, and then there's specific CPU interfaces. Build a chief tracker for model aviation. Oh yeah, I was in the drone world. Just put a BLE beacon on it. I don't know. Yeah, so the signals get gated by the distributor for the global thing, and then there's a target. So it's a bit mask of what CPUs want to hear about a given interrupt. So if we look at the distributor and we find the targets, we can see targets here. And we can print that out, and then I'm not sure, we must be in this bucket here. It's 8 bits, so this one value is a 1 in the one spot, which should, I thought, set the target bit for the core 0 for USB. But once it goes there, then it goes out to the CPU interface, which is the GIC CPU, which we can look at the control register to make sure that that signaling of group 0 is enabled. Which it looks like it is. Interrupt acknowledged. So this is the register you read to figure out what woke you up. And then it turns out you actually write that back to tell it when you're done, which is new. And what that will do is then that will clear the interrupt for everyone else as well, which is interesting. We can see there's this ID register that we know is valid because I added the enum, which is good. So in a world where you can like mess up your addresses, it's nice to have those like identifying registers just to feel more confident. We can see that there's this highest priority pending interrupt. So this is a way to see like what you're going to do later, or what you would do now if you did this interrupt acknowledge. The 1023 is a value that says like nothing right now. It's called a spurious interrupt, and that can actually happen. Like, say you have an interrupt coming in and there's 2 processors that are trying to handle it at the same time. What can happen is like one will get it and the next one will, it will have been interrupted, but the one that it reads will just be a spurious, and it's supposed to just go back to what it's doing. So that looks right to me. I wonder, like, we're running in EL2 non-secure mode. And there is some complexity. So if we look at, yeah, 1023 is a magic number. It's a magic number to say that it's a spurious interrupt. And I know that because in so there's this PDF, the GIC v2 spec. It's what tells you like how to handle stuff. I wonder if we could just search for 1023. A processor reads the GICC, so the second C there is for CPU, obtains the interrupt ID 1023, indicating a spurious interrupt. The processor can return from its interrupt service routine without writing to the end of interrupt register. It indicates the original interrupt is no longer pending, typically because another target processor is handling it. So that's kind of like that race condition thing. And they actually had two types of interrupts. The 1 to N is the like only one person needs to handle it, and then there's also N to N, N to N, which means that like when it happens, all the processors need to deal with it. And oh, this is kind of a nice diagram for like how the state changes for interrupt. So like inactive, and then it goes to pending, and then it can either go to pending active or just active, depending on what happens. Have a good one, John. There's a lot of past episodes, and I've been doing this quite a while. But for the Raspberry Pi stuff, I think there's maybe like 3 or 4 episodes, so you could catch up with the Raspberry Pi stuff. This is the first day we've talked about interrupts, though. We were talking about other stuff before. So the question is why oh why are we not actually getting into the interrupt handler? Because, well, it's not being marked as pending. Let's go over the distributor register model processor targets. These registers are byte accessible. A register field corresponding to an blah 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 reads as 0. GSID target SR 0 to 7 are read only. IT line numbers +1. CPU targets. Right, so like bit 1 is. Oh yeah, P-Boy, that's a good idea to do those show notes. I bet you got blocked, so I will post it. Spook, do you want to go out? Yeah. Why don't you come up here? Come on. He's meowing at me. You probably can't hear him meowing at me. So it doesn't seem like we're seeing it as pending. We're seeing it as pending in the come on. We're seeing it as pending in the distributor, but we're not seeing it as the next thing to hit the CPU interface. So maybe there's more to it than that. Maybe there's something else. Meaning of CPU targets bit field bit values. Like bit 1 is CPU interface 0, which we should always just be on CPU 0. Hi, kitty. The corresponding GICD target is M, or interrupt ID M divided by 4. I mean, we can double check this. The offset is that. The byte offset of the required priority field. Required priority field. I left all the priorities as 0. I wonder if that's not valid. What does priority say? If anybody has final questions, go ahead and ask them. I'll probably wrap up pretty quick here. Corresponding to an unimplemented interrupt reads as 0. Like 0 is the highest priority, but maybe... Oh, interesting. The priority registers are banked for each processor. Oh, no, just the starting ones. Have a good one, Minnesota Mentat. Yeah, we're just about to wrap up. It's actually interesting that like viewership drops after the 2-hour mark. From an implementation defined range. The lower the value, the greater the priority. But I wonder if it's... I wonder if 0 is invalid. Let's look at the... So the implementation docs are here. Programmer's model. Distributor. What does it say about priority? Anything? I could try setting it to like 1 and just see if that works. Yeah, it doesn't tell me. Tell me that. Can you display the priorities with the SVD command? Yeah, I can do that. Didn't I do that? I did target. I did pending. Did group. Oh, did I not do priority? All right, let's do it. It's in its own cluster. And then, oh yeah, I mean, it's all 0. But I don't know if Robotrix -2. Mototimo is asking, just received the ESP32 C3 dev kit. Where are we with possible CircuitPython support? There's 2 C3s already supported in CircuitPython. They do use the UART interface, so they have a big warning that they're not proper CircuitPython. But I believe that Microdev is working on BLE support. So the plan with C3 is you'll be able to do the BLE workflow stuff. Yeah, so right now it's just priority 0, but I just wonder, let's just, as a Hail Mary with 3 minutes left here, I wrote the code to set the priority, so let's just try setting it to 1. Just to see if like 0 is invalid. I don't think so. It doesn't make sense to me, but let's just try it. Beely will be nice. Yes, Melissa's been working on code.circuitpython.org as well. Okay. Make. Copy it over. Home repos, TinyUSB, examples, device, CDC, mass storage, build, Raspberry Pi. Copy it over to boot, overwrite it. Safely remove, which kills my desktop thing for some reason. Every time. Yeah, the IDF has been updated. Or for the S3, I don't know if we're, I don't know. I don't know what version we're on for that. Okay, so we got our mass storage out, but we'll start it back up. We'll blink. Do OpenOCD and see where we are. We're in fifo-read. And if we look at the priority registers, they're all 0 still. Is that true? Even though I thought I set it. What number is it? We think that the USB interrupt is, oh, come on. $105. Good night, Deshipu. I mean, that's a little interesting that it's still 0. -1. Okay, well, let's wrap up. I might keep poking at this. We'll see. I don't know. It's weekend. Thank you all so much for joining me for another deep dive here on the Adafruit YouTube channel. If you want to support me, you can do so by supporting Adafruit by going to adafruit.com, purchasing some stuff there. Check out, maybe they have some Adafruit or some Raspberry Pi, Pi 4 stuff that maybe we'll get this working with at some point. Once we figure out why it read 0, which is weird. That is intriguing. Thanks again to DCD for doing notes, and thanks to Ask Patrick W for making sure that they end up in the notes repository. Let's see what else. This is Deep Dive. Next week should be at the same time on Friday, 2 p.m. Pacific here on the Adafruit streams. Join us on Discord if you want to chat with us throughout the week. You can go to the URL adafru.it/discord to get into the Discord. Follow those 2 repos that should be in the description to check out the work as I do it, and help me out if you want to help me out. That would be awesome. Follow along, that'd be cool too. I think that's about it. I'll go to cat cam and pet the cat because he wants some pets, and then we'll call it. So thank you all. Have a great weekend, and we'll see you next week. Yeah. Cat cam. Kitty, kitty. You're up and about.